This chapter deals with kinetics, and so what we're going to do in chapter 14 will be kind of in contrast to what we're going to do in chapter 19, where we talk about thermodynamics. So chapter 14 is basically a way that we can see how fast a reaction will go, as opposed to chapter 19. Thermodynamics will tell us whether it will even happen. For this chapter, we're going to see that there are different rates that apply in different kinds of reactions, and those depend on how the reaction occurs. Many of the reactions in this chapter can go in both directions. They can go in the forward direction, and then to some extent they'll go in the reverse direction. Actually, that happens to a lot of these reactions, but because they're primarily going in only one direction, we'll just draw an arrow showing them going in one direction. But just be aware that some of these reactions that show arrows only in one direction can also go in both directions. They can also go in the reverse direction. And so we'll talk more about that when we get to chapter 15, which is equilibrium. As always, I want to give credit, and the main credit here for these lecture notes is going to go to Brown and LeMay's chemistry and to Zumdahl's chemistry. I think most or a lot of these lecture notes came originally from a set of slides that were put out by Zumdahl. A lot of the commentary and there's a lot of what's actually on the slides, including some of the slides themselves, were put in by myself. But the basic framework that it started with was originally Zumdahl, and even before that with McMurray and Fay. So I want to give credit to them, but the commentary is provided by myself. So let's skip over the next couple of slides. So you can pause these if you want. Okay, so for this chapter, mainly what we want to worry about is the rate laws. So that's going to be the first thing here. So each of this, there are actually 3 of these, and for each of those, there's going to be what you'll mainly want to focus on for each of the 3 different rates, which is that there are 3 different ways that reactions can happen. Actually, there's more than that, but we're going to focus on only 3 of those because they're the most common. And they're referred to as 0 order, 1st order, and 2nd order. And for each of those, you'll want to be able to do problems that deal with what are called the integrated rate laws for those 3 rates. So each of those rates will have its own integrated rate law, and they're very similar. It's just that there's a slight change as you go from 0 to 1 and 1 to 2. And then also for each of those, there's a certain way that you figure out the half-life. And what that means is, in other words, you figure out how long it would take for a certain amount of reactant to go to 1/2 that amount. And those are called the half-lives. Each of the 3 different kinds of reaction has its own formula for figuring out what the half-life is. And we'll deal with some of the derivations of some of these, but you don't really have to know that. And then we'll look at reaction mechanisms, which will lead us naturally into the Arrhenius equation, which we'll look at. Basically, that'll be the last thing we'll do. So let's go to the next slide. So let's look at some of these rate laws. Next slide. So first of all, we can say that the rate of a reaction is the change in the concentration of the reactant. And if you have more than one reactant, then you can do this with either of the reactants or any of them over the change in time. And the way that you can write that is you can write rate, which I'll just put R here. So I'm just bringing this down. Rate equals the change in the concentration of A. So first of all, when you see that delta there, that means change. That's capital Greek letter delta, and then the brackets indicate concentration. So that would be called either concentration, or they may call it molarity. In other chapters, they may call it solubility. They're all the same. So whenever you see the brackets, it's talking specifically about molarity, moles of solute per liter of solution. So it's just the change in the concentration of some reactant A, or it could be a product. But for various reasons that we'll talk about later, we usually use reactants. Next slide. So for this reaction, we start with A and we produce B. A is the reactant, B is the product. The arrow is going in one direction, even though, as I mentioned at the beginning, a lot of these reactions will actually go in this reaction in this direction as well, but they're primarily going in one direction. If not all the time, then at least at the beginning. Um, and so we're just going to deal with the forward direction in this chapter. In chapter 15, the next chapter, we'll talk about what happens when you have a reaction that's basically going in both directions. So let's go ahead and move on. So for this reaction, we could write this that the rate equals the rate of disappearance of A over the time. In other words, we could write it as the change in the concentration of the A here over the change in time. That would be the rate. So we could write it as the change, the delta A, or delta concentration of A, over change in time. However, think about it for just a second. This is a reactant, so its concentration is actually going to be going down. So if you started with 4 moles per liter, at some point it would get to 2 moles per liter, which that would be what we would call its half-life. But because it's going down, then you put a negative sign in front of it. So you would write it as the rate is negative delta A over delta T. Let me say it this way. Another way we could write that would be, instead of writing delta A over delta T, we can write this as dA over dt. And if you haven't had calculus, you wouldn't be familiar with this, but the D it just stands for a differential, or a tiny amount of A or time or B. So I'm going to put a bracket or a parenthesis around this part over here. So we could either write that it's the change of A with time that's minus, or we could write it that it's the plus change in time of B. But we usually just worry about this part. We usually just write it in terms of A, not in terms of B here. These are going to be the same anyway if this is a 1 and a 1 here, but at least initially. But so we usually just pick this one and use this one. So we can write this one way as just minus the change in the concentration of A with time. Okay, let's go to the next slide. So what we just talked about was called the instantaneous rate. In other words, at any particular moment, the rate would be the minus the d, lowercase d, concentration of A over dt. So in other words, it's the rate at a particular moment in time. And again, if you haven't had calculus, you won't understand this, but in calculus, one of the first things you learn is that if you take the slope of a curve at a certain point, that's called the derivative at that point, and that will represent the change at that moment. And that's what we're dealing with here, is the change. Let's go to the next slide. And then there's another way we could write it, and that is to write it where the rate of this reaction is equal to some rate constant K times the change in the concentration of A. And for the reasons that we'll see later in this chapter, okay, so we can write this as that the rate, and this is different from what we did before, okay, so we can write this that the rate is some rate constant K times the concentration of A. And what we're doing here is we're just writing this. We start off that the rate of this thing is actually proportional to the concentration of A, and then we change that to an equation, so we write this as rate equals K times the concentration of A. But because there are 3 different ways, actually more than that, but for our purposes, 3 different ways that these reactions can occur, we have to take each of those into account. So we could write this 3 different times. We could write it as rate equals Ka to the 0 power, or we could write it as rate equals Ka to the first power, or we could write it as rate equals Ka to the second power. So in order to keep from having to write this equation 3 different times, we just put an N here above the concentration of A, and that N can either be, as it says down here at the bottom, it can either be 0, 1, or 2. All right, so this is the way we call writing a rate law. The rate equals some rate constant K times the concentration of A to the N power where the A is your reactant. And so here, this N would have to be determined experimentally. Also, the rate would have to be determined experimentally, and also the K. Okay, next slide. Here's an example of a reaction that turns out to have that N here is 2. So this would be called a second order reaction. So here we see that there's a rate here that equals 0.255, and then there are some units here. And then the concentration here of our reactant, which in this case is NO2, is raised to the second power. So you do not want to just look at this 2 and say, okay, well, for NO2 it's going to be second power, because it doesn't always happen that way. So you can very easily get the answer on a question wrong if you do that. So don't do that. So all of these things, as we said before, have to be found experimentally: the rate and the K, and also the exponent N. Let's go to the next slide. And so whenever we do these kinds of problems, we always want the disappearance of this reactant A to be in moles per liter, because that's the units of concentration. And then, since it's over the change in time, we want it to be in moles per liter per second. So the way that that's written is moles per liter times seconds. And so all of these, whether they're zero order, first order, or second order, we still want them to wind up with these units. But they wouldn't, for example, if it were zero order or second order, they wouldn't end up in moles per liters per second. So what we have to do is make them end up in moles per liters per second. So what we have to do is change the units on that constant K. And we can do that arbitrarily. So we just do that such that the units always end up as just being moles per liter per second. Let's go to the next slide. And here is the same example we looked at a moment ago. This slide probably should actually have been previous to the one before, but anyway, here are the actual data points for that reaction, and you can look at this if you want to. Let's go ahead and move on to the next one. And then here's another picture of this where we're plotting the concentration of that reactant that we looked at a moment ago versus time. And you can see that data here. Let's move on. All right, so what I'm going to do now is the first derivation. So we can write that for any main reaction, for example, for the one that we just looked at, the rate is going to be some rate constant K times the concentration of the reactant. In this case, that's NO2, raised to some power N, where N has to be 0, 1, or 2. And again, to go back to that N, the reason it has to be 0, 1, or 2 is because there are 3 different ways these things happen. And each of those corresponds to raising the concentration to a different power. And the reason they happen differently is because reactions happen differently. Like sometimes you might have a reaction for one thing breaks up into 2, or 2 things could go to 1, or one thing could react with another thing and produce another thing, or one thing could react with another thing and produce 2 other things, and so forth. Okay, the other point that it mentions here is that we're going to take these measurements at the beginning of the reactions. In other words, before any product is formed. In other words, what we want to do is we want to mix the reactants together, or if there's only one reactant, just put the one reactant in there. And then we want to immediately take the rate measurement, like at the very beginning of this process, because if we wait, as I mentioned before, a lot of these reactions have a reverse component to them, where that if you let them react for a while, then you'll start to have some of the product going back to the reactant. And so that actually would be an equilibrium, but we don't want that. We want the rate at the beginning. So we take the measurements for the rate determination at the beginning of the experiment. Okay, next slide. So for example, for this reaction, we have the rate, and this is the same thing as we had on the previous slide. The rate is some rate constant K here, times the concentration of the reactant here, which is NO2, raised to some power N. And again, as we said before, the N would have to be determined by experiment, as would the K and as would the rate itself. Okay, next slide. And so, as we've said before, the n, the exponent n, and the k and the rate all have to be determined by experiment. Next slide. So there are two different kinds of rate laws, of which we're going to use this kind at the bottom. So integrated rate laws are rate laws where you've done an integration of a differential rate law, and that won't mean anything to you if you haven't had calculus, so I wouldn't worry about it. But the bottom line is that we're going to use what are called integrated rate laws. But some books, especially more advanced books, will talk more about the differential rate laws. And they can be converted back and forth, so it doesn't really make that much difference which way you write it. But if people don't understand what you mean, for example, by that, then it's better for you to write it in a way that they do understand it. So hopefully most of you guys can understand this, even though it's an integrated rate law. The result of that integration of something like this on the top here is that you end up with something like this. So you'll either end up with just like something like this, which would be the logarithm of AT equals minus KT plus the logarithm. But you know how to do logarithms, right? Whereas some of you may not know how to do derivatives. So this part right here of that rate law is a derivative. But you do know how to do this. So we'll write them in a way that you do understand how to do the problem. And then if you, at some point, if you take calculus, then you'll start to understand some of the other stuff. So all of the three different rate laws for the three different rate orders, 0, first, and second order, all of the integrated rate laws can be easily understood and done by, just about anybody that has a basic understanding of math. So that's how we're going to write these. So there will be three of these integrated rate laws, one for 0 order, one for first order, and one for second order. But just be aware that you can also write them in a differential form, and they're interconvertible. So you can go back and forth from one to the other. And this is what it would look like if you did it that way. Okay, so next slide. And we've already talked about this, so let's go to the next slide. We usually, whether we write it, in our case, we're going to write it in the integrated rate laws. So let's go to the next slide. So this slide is just saying something that I've already mentioned. We want to start off measuring the rates and everything as close as possible to the very beginning of the reaction. Next slide. So let's look at some examples. I'm doing A plus B is C, where the A, B, C don't stand for anything. They're just like just things we're using symbolically. And then we'll look at D, E, F, and G, H, I later on. So let's start with the A, B, C thing, and we'll learn a little bit about how to find the orders and so forth. So let's go to the next slide. So here's an example, and I think it's easier for you to see what's going on with these. So here we have two reactants, and then we have some product. Remember, we're not going to worry about the products. We're just going to worry about the reactants, because we just want to get the rate of the reaction by seeing how fast the reactants disappear at the beginning, as close as possible to the beginning. Okay, so the way you do these problems is you look to see which thing's being held constant, because you can only do one of these at a time. And so in this case, A is being held constant. So we're doing three different experiments, or they may be referred to as runs. And in each of those, we're keeping the concentration of A at 1. So the concentration of A is not changing. What we're changing is B. So between this run and this run, we double B. And between this run and this run, we triple B. So we look over here to see what happens to the rate. And so if we look over here at the rate doesn't change. So we double the concentration of B, and the rate doesn't change. And then we double the concentration, or actually we triple the concentration of B from the beginning, from here, and the rate again doesn't change. In other words, what we're saying is that it doesn't really seem to matter what we do to the B. The rate of the reaction doesn't change. So in other words, it seems like the B doesn't really matter. So when we have a case where the reactant doesn't matter, we just say it's 0 order. In other words, it doesn't affect the rate at all. So for example, here we would say that the reaction is 0 order in B. So let me just write that. This is how we would write this. So the order for the concentration of B would be 0. So you put a 0 there. So this is where we had written N, right? So in this case, the N would be 0 because this is 0 order. The reason it's zero order is because it doesn't have any effect on the rate of the reaction. So if you think about it for a moment, if you didn't know this already, any number raised to the 0 power, you may recall, is always 1. So any number that you put in here for B, if you raise that number to the 0 power, it's always going to turn out to be 1. So when you have your rate law, you're going to have rate equals B to the 0 power, which is just 1. So in other words, what happens is in the rate law, which it would actually be K B to the 0 power, so it would just wind up being rate equals K times 1, which would just be rate equals K. Okay, so that's for zero order, and we'll come back to the units in a little while. Next slide. Here's another example. Here, this time, we're keeping B constant. So B isn't changing, and we're changing A. When we double A, we look over at the rate over here at the right, and the rate doubles. So it's behaving the same way the concentration of A does. Then the same thing if we triple A, then the rate triples. So again, it's behaving just like the concentration of A. In other words, there's like a one-to-one correspondence here. And so it's first order in A. It's first order in A because every time we double the concentration of A, we double the rate of reaction, and so forth. So this one would be that the rate would be some rate constant K, and this is the way you write a rate law if you're asked on a test to do this. Some rate constant K times the concentration of A. Excuse me. Actually, what I should do is I should pause these while I do this writing so it doesn't waste time on the video. But anyway, so the N, where I just wrote that 1, that's where the N used to be, right? So the N here is 1. So remember, if that N is 0, it means the reactant, like the B in the previous example, doesn't have any effect on the rate. But here it does have an effect. It has an exact effect so that every time you double A, you double the rate. So we call that a first order, and we write that as a 1, a first order reaction. Next slide. Let's do another one. What's being held constant here? D or E? So look at that for a moment. It's D. So we aren't changing D, but we're changing E by doubling it. And notice over on the right, if we double the concentration of E, and notice here, this is not the ABC, which we're changing to a different example. The rate doesn't double, it goes up by a factor of 4, which is 2 squared. So the 2 here you can think of as if you double it, you write 2, and if you triple it, you write 3, and so forth. And what happens is it goes up by a factor of 4, which is 2 squared. So the N here is going to be 2. So you would write this as rate equals some rate constant K times the concentration of E to the second power. So and that's it. So it's either going to be one of the 3 examples we just looked at. So it's either going to be rate equals K times some reactant to the 0 power, or to the first power to the second power. Now, we didn't talk about it before, but if you have a 0 order reaction, the rate stays the same. So you could say that that's kind of like if you doubled it and the rate stays the same, that, in other words, you multiply it by 1, that would be 2 to the 0 power. And if you double it and the rate doubles, then you're multiplying the rate that was originally there by 2, which is 2 to the first power. So you have 3 different possibilities, either 2 to the 0 power, or 2 to the first power, or 2 to the second power. So that's where the 0 and the 1 and the 2 come from, that we write for N. It's the number we would have to raise 2 to get what we would multiply by the rate. In this case, we'd have to multiply the initial rate by 4, which is 2 squared, to get it to 0.2. If you tripled it, you would do it the same way, except instead of writing a 2 here and here and here, you would write 3. Next slide. Okay, and we've already talked about this. Next slide. So the way that we would write a rate law overall would be to write the rate equals some rate constant, K, times the reactants raised to some power that's either going to be 0, 1, or 2. So don't confuse this m here. That isn't anything different from the n that we have over here. It's either going to be 0, 1, or 2, and they can both be the same. So you could have a to the 1, b to the 1, or a to the 2, b to the 2, or you could have a to the 1, b to the 2. So when you add these two things together, whatever you get, like if it's 1 and 1, you'd get 2. We call that the overall reaction order. Next slide. Okay, let's do another one. So here we have two reactants, and you can look up at the top and see here's our reaction. So we're starting with G plus H. So we have two reactants, G and H. So we list their concentrations here, and then the rate over here. So this would be a typical way you would do a problem, except the numbers won't be as easy. And here we have 1, 1, and 2, and 1, 2, and 1. So in other words, we don't have a way we can just keep one thing constant for the whole thing that we're going to do here, but we can keep, for example, here for the first two runs here, notice G is constant. So let's just call that run 1, and this will be 2, and then this one here will be 3. Then for the first two runs, we're keeping G constant. It's 1 in both of them, but we're doubling H, and the rate over here doubles. So that means that in H, because that's the one we're changing, in H, if we double H, the rate doubles, so that means that it is first order in H. So let's just write a 1 here by the H to show that it's first order in H. And I'm just doing this the same way we did before. Now to keep H constant, we have to use runs 1 and 3, where they're both 1. We can't do it any other way. And if we do that, then we're going from 1 here for G to 2. So we're doubling G, but the rate is going up also by a factor of 2. So that means that this reaction, G plus H plus I, is also going to be first order in G. And so this is the way you will actually get your problems on the tests. So look at what happens when you keep one thing constant and you change the other thing. The thing that you're changing is what you're trying to figure out the exponent for. So for both of these, we have a first order reaction in that particular thing. So it's going to be rate equals some rate constant K times the concentration of G to the first power times the concentration of H to the first power, where you can just leave off the ones, right, because anything to the first power is just that thing. So you could just write it rate equals some rate constant K times concentration of G times concentration of H. And that would be your rate law for this problem. So on a test, if they ask for the rate law, that's what you put. And then the overall reaction order would be 1 plus 1, because it's G to the first, H to the first, which is 2. So the overall reaction order will be 2. Next slide. All right, so let's look at a quick concept check. How do the exponents, or the n numbers in the rate laws, compare to the coefficients? And the answer is they don't. So again, the warning here, don't look at the coefficients in front of the reactants and assume that that's what the reaction order is going to be for that reactant, because it won't be in many cases. Next slide. All right, so deriving the integrated rate laws is something that I'm going to let you guys do if you want as an exercise. You don't have to necessarily have had calculus at this point, but if you're going to take it, and really this isn't calculus, it's actually differential equations. So that's the course you would take next after the 3 calculus courses. So you would take calculus 1, calculus 2, calculus 3, and then differential equations. And then to do certain types of engineering, you would also want to go ahead and take partial differential equations. So what I'm going to do is derive these, and so I'm going to go through this kind of quickly because I'm going to anticipate that most of you won't really want to worry about this too much, and you don't have to because it's not going to be on the test. But let's do it. So next slide. So for zero order reactions, what we do is we start off with, first of all, rate equals some rate constant K times A to the 0 power, where we've gone ahead and put the 0 in here because we're assuming here that we're deriving this for zero order reaction. And then we can also write it the other way we said, where we write it as rate equals minus dA over dt. And what we're going to do is, since there's a rate on both of these, we just set these things equal to each other. So we set the K times A to the 0 equal to minus dA dt. Okay, so here is your integrated rate law for zero order. It's A sub t equals minus kt plus A naught. And these will be given to you on your formula sheet. Whoops. However, I strongly recommend that you just memorize these because it will make it much faster for you to be able to do the problems if you don't have to keep looking these up. Okay, A sub t means the concentration of A that's left over after a time t has passed. K is just your rate constant. The minus sign has to be in here. T is the time that has passed, and A naught, or A sub 0, is the initial concentration of A. So for zero order reactions, this is your integrated rate law. And this is what you're going to need to be able to do most of the problems of this type. There will also be a half-life associated with zero order reactions, which we'll get to in a minute. So again, if you want to memorize this, now what I'm going to do next is I'm going to derive this. So if you want, you can just skip ahead a couple of slides after this slide. Notice that the way this is written, it's done this way intentionally so that it's written in the form of a straight line, so that we can identify the y-intercept as A naught and m as minus k. And that's going to turn out to be pretty useful, because if we have a graph of this particular reaction, in terms of, like, after so much time has passed, the concentration has dropped to this point and so forth, and you make a graph of it, then if you get the slope of the graph, that actually is going to equal minus the rate constant, which means that's an easy way for you to figure out the rate constant. And also, for some of the problems that we'll get, that'll actually be the only way you can get K. So, I mean, there are other ways that you can get K if you're given other information, but if you're only given the slope of the line, either by just being told this is the slope of the line, like if it's -2 or whatever, or another way they can do it is they can give you the graph and make you figure out the slope. So to do that, you would just do the rise over the run. Anyway, so for a zero order reaction, this is your integrated rate law. A sub t equals minus kt plus A naught. Okay, and then let's go to the next slide. So what I did here, this slide in a couple of, maybe one or two more you can skip, I just set this equal to this, and then when I did that, I got this, and that is a differential equation. It's an ordinary differential equation. You don't have any partial derivatives in here. And then I used, without going through a lot of detail, you can read this if you want on your own, I used the technique that you learn usually second when you take differential equations. Usually the first technique you learn is just where you use basic not algebra, when you use basic calculus and just like solve the problem with calculus. This one you can't do that way because you have to do some rearranging that you would not have really learned in calculus. And what you're doing is you're getting all of the variables of one side on one side of the equal sign, and then getting all the variables of another side on the other side of the other variable. And I mean, obviously this technique doesn't work for everything, because you can't always do this, because some differential equations cannot be separated, and then you have to use other techniques like using an integrating factor or something like that. Okay, so anyway, we set these equal, we rearrange here, and my purpose is not to go through this. So I just put this in here. I just derived this so you can see how it's done. Next slide. So anyway, here's some of the math I did to figure this out. And then I take the integral of both sides after I pull everything out that's constant. And I end up here with this. So this, I actually wrote it as a definite integral, but you don't have to do that. You can use indefinite integration and just use A naught as your constant of integration if you want to. And this is what we come up with, and this is what we had 2 slides back, I think it was. So this is the integrated rate law for zero order reactions. It's A sub t is minus kt plus A naught. Again, I would memorize that. Let's go to the next slide. So if we plot the concentration versus time and we get a straight line, it means it's zero order. So this is another way where we can tell the order. So notice here that for this particular reaction, they just plotted the concentration of A as time goes by on the x-axis, and they get a straight line. So that means it's a zero order reaction because we're plotting the two things that are in the zero reaction, the zero order reaction integrated rate law. And that is just the concentration versus the time. And you'll see that better when we get to the next two. That is when we get to the first and second order reactions. Okay, and then we still have to talk about the half-life. Let's go to the next slide. So for zero order reactions, the half-life looks like this. It's whatever the initial concentration was divided by 2 times the rate constant. Okay, so we're going to wind up again with 3 different equations for half-life. So we'll have 3 equations that are the rate laws, which are probably the things you'll use the most, but we'll also have problems where we'll have to know the equation for the half-life for all 3 of the different orders. So we'll have one for zero order, and that's what you see here. And then we'll have one for first order, and we'll have one for second order. For all 3 of those, one of the things that will help you to remember these a little bit, although they will be on the formula sheet, is that K is always in the denominator. So for zero order, which we see here, it's 2K in the denominator, but the K part without the 2, so for this one, it's actually 2K, but for first order, it's just K, and second order, it's just K. So anyway, K will always be in the denominator. So what's actually going to change is what's on top and also what's beside the K. So for zero order reactions, the half-life is that the T1/2 is A0 over 2K. That'll be on your formula sheet. And this equation is useful if you know what the initial concentration is and also the half-life, then you can figure out what K is. Now for zero order reactions, well, let's wait and talk about that later. All right, so notice here that as time goes by, A0 is going to get smaller and smaller. So every time you have another half-life, you're going to have half as much A0 as you had before. So the half-life will also get smaller. And that's something you could see on a test. For zero order reactions, as time goes by, the half-life gets shorter. And just to go ahead and anticipate the next two, for first order, I'll just tell you that the half-life doesn't change. It's constant. And I'll review these in just a moment, so if you're not sure what's going on. For second order, they get longer. So let's just go through these again. Here, for this one, the half-life gets shorter as the concentration decreases. In other words, as the reaction goes on. So for zero order, the half-life will get shorter. For first order, which we'll talk about in a minute, it stays the same. And for second order, which we'll talk about last, it gets longer. And again, we're talking about the half-life. What do we mean by the half-life? The amount of time it takes for this thing from, say, 4 moles per liter to go to 2 moles per liter. That's, in other words, to go to half its original value. Next slide. And so here is a derivation of what we just did. If you want to look at this, you can pause the video and just read this for yourself. We start off with just some basic equations, and we end up with what we just said. The half-life is the original concentration divided by 2 times the rate constant. Next slide. All right, and then so here's your integrated rate law for zero order. Next slide. Let's go to first order and do the same thing. So next, so here is your rate law, or your integrated rate law rather, for first order reactions. When we say first order, we mean that that N number right there is 1. It is just like the zero order reaction or equation, except that we have a logarithm here in front of the first A sub t, and we have a logarithm in front of the A0. Otherwise, everything else is exactly the same. So that's again why I recommend you just memorize these so you don't have to keep looking it up. But again, it will be on the formula sheet in case you forget on the test. Okay, again, notice here that we've got this y equals mx plus b thing, just as we did before, but the y and the x are different. Well, the x is the same, actually, because the x is still t, right? So that x right there corresponds to our t variable here, but the y has changed from just the concentration of A to the logarithm of the concentration of A. And you may be thinking to yourself, you can't take the logarithm of anything except just a pure number, and that's correct. So if you have a concentration in moles per liter, you just have to get rid of the moles per liter to do the concentration, and then take the log of it to do the log of the concentration, logarithm. And then you have to resupply the units at the end. Okay, let's go to the next slide. Here's our next derivation, which I've just done for you to show you how to do this. And it's done kind of similarly to what we did before, but the integration turns out to be a little different. Let's go to the next slide. So here, the integral of 1 over A is the logarithm of A. So that's where the logarithm comes from. So if you've had, like, I guess the first, or maybe it would be the second semester of calculus where you talk about the integral of 1 over x is logarithm of x. So if you've had that, you'll see where that logarithm rather came from. Again, you can do this either as a definite or indefinite integral. And I did it as a definite integral, but you can just also do it as an indefinite integral and then let this be your constant of integration, which that's just typical procedure. Anyway, so the bottom line is here is the first order integrated rate law. And we're going to have a half-life associated with this also. And that is going to be that the half-life for first order reactions, and it's on a slide following, but when we get to that slide, we'll just skip it. The half-life is going to be 0.693 over K. And I'm going to just write this as 0.693 to save time. In fact, I'm going to try just pausing it and writing while I pause. Okay, so we're back on, and I wrote this formula out while we were off. And I'm just realizing now, after I've already finished all the videos, I'm realizing that I could have been doing that the whole time. But anyway, so the half-life is 0.693 over K. I hope I didn't mess this thing up by doing that, but anyway. We'll get to this also in a minute. This 0.693 is just the logarithm of 2. So you could also write it as logarithm 2 over K. And this one won't change. So for this half-life here, it's constant. There's nothing in here that deals with any kind of concentrations. So there's nothing changing. We just have a number over a constant, which is a constant. Okay, so these problems are done the same way as they would be done for zero order, except you have to take the logarithms. All right, next slide. So the next few slides, I'm just going to start skipping through here. So next, and here's a plot. This time notice that we're taking not the concentration of N2O5, but the logarithm of the concentration of N2O5. We're plotting it against time, and we're getting a straight line. So that's telling us this is a first order reaction. Now, if we had plotted just the concentration of N2 over time, N2O5 over time versus time, we would not have gotten a straight line. And I don't know exactly what it would have looked like, but it wouldn't look like this. Anyway, that's how you can tell by a graph that this is first order. Next slide. And then we already said this, so I'm just going to kind of go past it kind of quickly. The half-life for first order is going to be 0.693 over K, where that 693 is the logarithm of 2. And what I said earlier, it does not depend on the concentration. Next slide. Here's the derivation for the half-life. So you can stop and look at that on your own if you want to. Let's go to the next slide. All right, here's a sample problem. So it says a first order reaction, which is what we were just talking about, is 35% complete at the end of 55 minutes. What is K? All right, here, this is a kind of a problem which we don't have very often, but you have to supply your own numbers basically for this one. So when you get a problem like that, what you want to do is you want to make your numbers as easy as possible. So I recommend starting with the first concentration of 1, which would actually be 1 mole per liter, right? And then we know what T is because T is given to us here. So all we have to do is say, okay, if we started with a concentration of 1, this is going to be what we had at the beginning. So this is our A naught. So what is our a sub t going to be? Because we're trying to find the k. What would a sub t be? So the real question is, what is a sub t? And we can determine that because if we started at 1 and we've used up 0.35 of it, then what we have left is 0.65. So a sub t is going to be 0.65. Don't make the mistake of writing 0.35 here. 0.35 is how much we've used up, but we don't want how much we've used. We want how much is still left after 55 minutes. So t is going to be 55 minutes. So when we do our problem, we're going to wind up with a k value that's going to be in minutes in some way. So all you have to do this problem is do the integrated rate law, which I'm not going to write it out. I'm just afraid that this thing's going to stab me in the back and just like not work after I did what I did a moment ago where I wrote while it was paused. I'm kind of like paranoid about that kind of thing because I've had it happen before where I've excuse me, invested like an hour in making a recording and then lost it all because of a glitch. So I'm not, and that's no fun. So anyway, I probably won't do that again. But I'm just going to tell you what the rate law is. It's logarithm of a sub t. So in other words, in this case, it would be 0.65 moles per liter for a sub t, but we're just going to call that 0.65 because you can't take the logarithm of units. So it would actually be the logarithm, and that's the natural logarithm of 0.65 equals minus kt, where the k is what we're looking for. T is going to be 55 minutes, and then a naught, it would be plus logarithm of a naught, where a naught is 1. So the logarithm or the log of 1 is 0. So if you choose 1 as your a naught, what happens is that that last term just drops out of the equation. So let's go next to the next slide. And I think, oh no, okay. I put this in here for you guys in case you're interested. So if you need this, you can look at this. So like we said just a moment ago that the logarithm of 1 is 0, the log of 1 is 0. So I'll be mentioning these things as we go through the course. Next slide. Excuse me. So we ended up down here with the logarithm of 0.65, which is minus 0.43. And the time here was minus 55 minutes. K is our unknown. And this is 0 because that's 1 for a naught. And the logarithm of 1 is 0. Which is this, that's where this 0 right here comes from. So it just drops out. So it vanishes. So we have minus 0.43 equals minus 55 minutes times k, and now just solve that equation there for k, and you'll get that k is 7.80 minus 3 minutes to the minus 1. Now, why did we get a negative number here when we took the logarithm of 0.65? Does anybody know? Well, the answer is because if the logarithm of 1 is 0, and the logarithm of a number that's greater than 1 is a positive number, then the logarithm of a number less than 1 is negative. And 0.65 is less than 1. So you can check yourself as you do your own problems. If you're taking either the log, the base 10 log, or the natural logarithm of a number that's less than 1, it should be a negative number. Okay, next slide. I'm having trouble again with my thing that moves the slides forward. Next slide. All right, and then the last one here is, I'm just going to kind of cut to the chase. Here is the second order rate law, or integrated rate law. Actually, it's not the rate law. The rate law is this thing up here at the top. So I should be more careful. It's the integrated rate law for second order. And notice it has the same basic form as the zero and first order rate law, the integrated rate law, sorry. Except that now instead of a sub t, and they didn't write the t here, so I'll put it in. Instead of being a sub t equals minus kt, notice there's no minus, so that's one change. And then instead of being a sub t and a naught, it's 1 over a sub t and 1 over a naught. Otherwise, it's the same basic form. So it's not that hard to memorize all three of these. So anyway, this would be the form you would use for a lot of the problems for second order reactions. Second order where n is 2 here. Again, I've got the derivation of this on the following slides. And again, we're going to have a half-life expression where, let's see, the half-life is actually going to be 1 over Ka0 for this one. But let's hold off on that until we get to that. So let's just look at this for right now. So the integrated rate law for second order reactions is 1 over A sub t equals plus Kt plus 1 over A0. Next slide. Again, here's your derivation, which I'm going to just skip over. You can look at this if you want to. Next. And next. All right. And so next. Let's just go to the next one. Next. So here, notice this time they did this graph two different ways. First of all, we're dealing with C4H6 versus time. In this one, they did it with the logarithm of the concentration, and here they did it 1 over the concentration. And notice that we got the straight line doing it 1 over the concentration, so it's second order. So that's another way that you can tell this is second order, is because you get a straight line when you plot the reciprocal of the concentration versus time. If we had plotted just the concentration versus time, which they didn't do, but if we play like they did it over here, we again would not have gotten a straight line. So the only time we would get a straight line would be if we do it, or we do 1 over the concentration versus time. And we'll see some examples as we go through these and also through the work problems. Next slide. Okay, next slide. We've already talked about that. And then here is your half-life. So it's 1 over Ka0. So notice what's happening here is that as this goes forward in time, A0 will get less. Like, for example, it might drop from 4 to 2 over the period of one half-life. But since it's in the denominator, what that means is the overall fraction here is going to actually get bigger. Which means the half-life here is going to get longer because the right-hand side over here gets larger. And actually, we can even go a step further. For second-order reactions, we can make the statement that each new half-life will be twice as long as the one before it. And that's how they'll do some of the problems, how they'll phrase them, is they'll say in the problem statement that, let's say, your half-lives were 4 minutes for a particular reaction, and then the next half-life was 8 minutes. So you use that as a clue, and that may be the only way you can do the problem. But you would use that as a clue to say, aha, this is a second-order reaction because the half-lives are getting twice as long. And then knowing that, you would be able to solve the problem. You'll see that better as we go along. You'll see that better as we go along. Okay, so let's go to the next slide. And then this derivation is for the half-life for second-order reactions, which I'm not going to go through it, so let's move on. So this is just two different ways that we can write what we just said. 1 over A0 equals K times T1 half, or 1 over A0 times T1 half equals K. Anyway, I wouldn't worry about that too much. Let's go to the next slide. Okay, so here we have an exercise. Okay, so the first two parts, first of all, A here, write the rate law for this reaction. Where we look back up at the reaction, and we've only got one reactant, so it's going to be, and I'm not going to write it out, but hopefully you can understand it if I just say it, and then you'll see the answer on the next slide. So it's going to be rate equals sum rate constant K times the concentration of A raised to some power. So how do we know what the power is? Well, so let's look over here in the problem statement. It says the first two half-lives are, first of all, the first one is 25 minutes, and the second one's 50 minutes. And we notice the 50 is twice as long as the 25. So That's our clue. It's telling us that the half-lives are getting twice as long every time we have another one. That means this is a second order reaction. So the exponent is going to be 2. So it's going to be the rate equals some rate constant K times the concentration of A, because there's only one reactant, A, raised to the 2 power. So the N will be 2 here. All right, B says calculate K. So the integrated rate law here would be something that we couldn't quite use because we don't have enough information, but we can solve this part by using this equation for the half-life. So T1 half is 1 over K A naught. So if we want to know what K is here, then we have to put in the T1 half and the A naught. And it turns out you can do this one 2 different ways. So if you want to use the first half-life here, you can, and that one is 25 minutes. So you would put 25 minutes there. And then for your A naught here, you would put 5 moles per liter. So just put 5 moles per liter here and put 25 minutes here and solve for K, which means you're going to have to do some algebraic rearranging, which, I mean, I'm going to assume that you know how to do that by now. Or you could use this half-life, the 50-minute one. But if you want to use that one, you can't go back over here and use 5 for your A naught, because if you're using the second half-life, then by the time you start your second half-life period, your A naught will have gone down to half what it was before. So you would have to put in 2.5 moles per liter for your A naught if you're going to put 50 here. So either way you do it, and I promise it'll work this way, you're going to get the same answer. So you may want to do it both ways just to prove it to yourself that you do get the same answer. And then once we've done that, once we know what K is, now we have enough information to be able to use the integrated rate law. So now they're asking us to find what A sub T would be if we had let this reaction go for 525 minutes. So let's see, what do we know? Well, we could use this for A naught here, so we can go ahead and underline that. And we know what T is because they told us here in part C that the time is 525 minutes, and then we know what K is because we figured it out up here in part B. So the only thing that we don't know now is A sub T, so we have one equation and one unknown, so we should be able to solve it. And so let's go to the next slide. Okay, so write the rate law, next slide. The rate is K A to the second power. And again, we can tell that it's a 2 right here because of these 2 half-lives that are doubling. Next slide. Calculate K, next slide. So either way you do it, and the way that I did it here was I used the first half-life with the original A naught. So that's 50, I'm sorry, that's 5. And I got that it is 8 times 10 to the minus third, and that's liters per mole times minutes, which we haven't talked about the units yet. Next slide. Or if you use the second half-life, as I mentioned, then you have to change the initial concentration here from 5 to 2.5. Notice you get the same answer. Okay, anyway, so now what we've done is we've found K. So now we can use that in the next part. Let's go to the next slide. All right, so part C said find A sub T at 525 minutes. So we'll use our integrated rate law here. For second order, it's 1 over AT, KT plus 1 over A naught, where we know what A naught is, we know what T is, we know what K is because we found it above. So the only thing we don't know is AT. So substitute in your value for K. I mean, you can rearrange this at the beginning if you want. I don't think I did that here. So substitute in your value for K and T, and also for your A naught here. And that's going, when you do your math on the right hand side, here of the equation, when you do all of this multiplying and dividing and adding and subtracting, you're going to wind up with 4.4 liters per mole. But you'll want to make sure that you understand that. What I mean is you want to make sure that you can do that on your own. And I mean, do it on your own without looking at the answer here. But what you found there was 1 over AT, not AT. But what we want is AT. So cross multiply and you get that AT is 1 over 4.4, which turns out to be 0.23 moles per liter. So here is your answer. So a lot of this is just algebra. Now, before we go any further, I want to talk about the rate constant units. When you have a first order reaction, that means that you have the units raised to the first power. So it would be like a concentration of, let's say, 2 moles per liter raised to the first power would be 2 moles per liter. And when you divide that by seconds, you get moles per liter per second. And we said a few slides back, or several slides back, that's what we want. But for example here, this is second order. So when you multiply second order, moles per liter to the second order would be moles squared per liter squared, which is not what we want. We want moles per liter. So we have to multiply the moles squared per liter squared times liters over moles. And that reduces it back down to what we do want, which is moles per liter. So how can we multiply by liters over moles? We have to put that into the rate constant itself. So when we did the rate constant here, notice that what we did was we put moles per liter, and I'm circling up here towards the top. That M, capital M, stands for molarity, which is moles per liter, but it's to the -1 power. In other words, it's actually liters per mole, and that's actually built into the rate constant. So that when we multiply the rate constant times the concentration, then one of those moles per liter that we had originally will vanish, and we'll wind up just with moles per liter per second, or moles per liter per minute, or whatever. And we didn't talk about that with regard to zero order reactions, so let's do that now. So for zero order, because everything kind of goes away and vanishes because you wind up with rate equals k times 1, you don't have any units at all. So the k, which you could see this better if I could write it out, but for zero order, it's rate equals k times a to the 0 power, which reduces to rate equals k. So the k has to have units of everything, moles per liter per second. Everything has to be put on the k after the number of the k, so that when you multiply the k times it, in that case times itself, you're going to get the right units, which we want always to be moles per liter per second. Next slide. Okay, so I'll let you read this on your own. Next slide. So here's a summary of the half-life behavior for zero, first, and second order reactions. So for zero order, the half-life gets shorter the longer you go, or in other words, the longer you run the reaction. First order, the half-life is constant, and that includes radioactive decay. So radioactive decay is constant. And then for second order, it gets longer, and it specifically gets longer in that it is going to be that every new half-life is going to be twice as long as the previous one. Okay, next slide. So here's another concept check. How can you tell the difference between first, second, and zero order by looking at the graph? So the first part is if it's zero order, you'll get a straight line if you just plot the concentration versus the time. If it's first order, you'll get a straight line if you plot the logarithm of the concentration versus the time. And second order, you'll get a straight line if you plot 1 over the concentration versus the time. For zero order, the half-life is dependent on concentration. Half-life gets shorter. For second order, the half-life is dependent on concentration, and the half-life will get longer. And for first order, the half-life doesn't have any dependence on the concentration, so it's constant. And again, that would include radioactive decay. Next slide. Okay, so this is a very good summary. You have everything in here that we just said. You have the regular rate laws. Remember that if they ask you to write a rate law, not an integrated rate law, they just want you to write rate equals some rate constant K times the concentration of A to some power. The integrated rate law would be the three things that you see written here. So here are all three of those together. And then the plot needed to give a straight line. We just talked about that. The slopes are going to be the things that are in front of the t's. So for 0 in first order, it was minus k, and for second order, it was plus k. And the half-lives are given here at the bottom. The units that you would have to multiply times to get it to the right units would be just for 0 order, you have to put in everything. So you have to put in moles per liters per second. For first order, you've already got the moles per liter to the first order, so it's just 1 over seconds. For second order, you've got moles squared over liters squared, so you have to multiply by liter over mole to get it down to moles per liter, and then again times seconds. Next slide. So consider this reaction. AA gives products, and here is your initial concentration, and here is your K. And we're supposed to find A sub T after 30 seconds. I'm going to set this up and let you guys, I always do this, so don't feel bad that I'm singling you out. But I always let the students do this as an exercise. So your T is going to be 30 seconds. I'll just set it up for you. And you're given A naught here, and you're given K. So you're supposed to do this for 0 order, first order, and second order. And the difference is just going to be, you're supposed to find A sub T for each of these. And the difference is going to be that you'll just use a different integrated rate law for all three of these. So for example, for 0 order, you'll just use A sub T equals minus KT plus A naught. So it won't take you but a few seconds, hopefully, to do each of these. So I'll let you do these on your own. The answers are here. Next slide. So here are the answers. And let's go on to the next slide. Reaction mechanisms. Okay, so reaction mechanisms are the way that reactions really happen. So like you'll see a reaction written in your chemistry text, written a certain way where everything is like it all happens in one step. And maybe in a few cases that is really the way it happens, but most of the time, especially on the more complicated reactions, things will happen in 2 or even 3 or even more steps. So when we see a mechanism, and you'll do this if you take organic a lot, you mean you're breaking it down so that you're actually watching one step at a time what happens. And when you do that, when you break it down into its intermediate steps, you call those steps elementary steps, which these have some unique characteristics. And sometimes when you do this, you'll actually, in the process of doing the reactions, you'll produce a substance that doesn't end up in the final reaction, and that's called an intermediate. It's something that's made in one step and used up in another step. Like, for example, if you have a mechanism where you have 2 steps, then you might make something in the first step, like let's say NO3, and then you might use it up in the second step so that when you add all the reactants to the products, you wind up with NO3 or whatever on both sides of the arrow, which means you can just cancel them. And so they just disappear, so they don't end up in the final reaction, which if you don't understand it, you'll see that more as we go through this. But you'll want to remember this name, and we're also going to want to remember this so that we can compare it with a couple of other things that are similar. So I think we can go to the next slide. A lot of this stuff, if you didn't get it, we'll talk about it again. So for example, here we have a reaction that they're showing in picture form. So this is the way you would see this reaction written in your textbook, but this is the way it would really happen. And I mean, I think it's pretty clear why they do it the way they do in the textbook, because if you had to do all of this for every reaction, it would take up like half the space of a whole textbook, or maybe I'm exaggerating, but anyway, it actually happens this way in 2 steps. In the first step, you have an NO2, and you're adding it to another NO2 to produce an NO3 and an NO. But notice this doesn't match what we're going to wind up with here at the top. Then in the second step, this thing right here, this NO3,
reacts with a CO, and one of the O's comes off, the O's are the red things, the red spheres, and one of the red spheres comes off the NO3, leaving this as an NO2, and then the O goes on the carbon to make CO2. All right, so what we would then do is add everything on the left-hand side of the arrows from both of these reactions and write that down here somewhere. And then everything on the right-hand side of the arrow over here for both reactions and write that down over here. And then if there's something on both sides, we just get rid of it. So for example, we would end up with an NO3 on the right, and we would end up with an NO2 on the left. So we would, at the bottom down there, we would just cancel these. And then also, is there something else that we would have on both sides? Yeah, we would wind up with 2 NO2s on the left, and then we would wind up with 1 on the right. So we can cancel 1 NO2 on both sides. And so we wind up with an NO2 here, plus the CO here. And then over on the right-hand side of the arrow, we have the NO and we have the CO2. And that matches what we're trying to get. So when you do these mechanisms, like usually they're done by research groups and universities, but when they do them, what they're going to be looking for is they want to have a mechanism where you end up with the same thing you started with, which would be this. And also, you want to wind up so that the rate law matches the experimental rate law. So, for example here, if this really is the way it works, in other words, if this mechanism is correct, then the rate law can be reduced to saying that the rate equals some rate constant K times the reactants in the slowest step, because we're going to assume that the fast steps will happen immediately. So for example, here, in this example, if we assume that this first step here is the slow step, then what we would have for the rate law would be rate equals some rate constant K times the concentration of A, but then it would also be times, which in this case the A thing would actually be NO2 here, but there's 2 of them. So it would be rate equals K times the concentration of A, which would be NO2. So it would be rate equals K NO2 concentration times the concentration of NO2 a second time. Okay, so in other words, let me say that again more clearly, hopefully. The rate equals K times the concentration of NO2 squared. And so if you know the steps that this thing behaves by, that the mechanism reacts by, then if you can know the steps, and then if you can also figure out which of the steps is the slow step or the slowest step, and just make the assumption that the other steps will happen immediately after the slow step, then you can write the rate law by just looking at the one intermediate step that is the slow step. So what I did here was I said, okay, then the rate, if step 1's the slow step, the rate will be K times NO2's concentration times NO2's concentration a second time. K times NO2 times NO2, which is just the same thing as K times NO2 squared. And it turns out that when they did the experiments to find the rate law, they did get that for the rate law. They got the rate is K times NO2 squared. Notice here that the rate doesn't depend on the CO here, and that's because the CO isn't involved in this slow step here. Let's go to the next slide. So this is what we would have gotten if we had added those together, as I said, and we would have had NO2 on both sides. So the things in light blue here are on both sides of the arrow, so we just get rid of them. So we just cancel those out, in other words. So that one goes, that one goes, that one goes, and that one goes. And so what we're left with is NO2 plus CO on the left and NO plus CO2 on the right. And that's what we wanted. So that part's right. Let's go to the next slide. And then also, we were told in the problem statement, actually, even though I didn't read it to you, But if you'll just go back, you'll see that it was mentioned in the problem statement that the first step is the rate limiting step. In other words, it's the slow step. So we can write that the rate for the overall reaction is going to be basically determined by the rate of the slow step. And since we know that's an elementary step, not an overall reaction, then we can write that the rate equals some rate constant K times the reactants involved in that slow step, which in that case was NO2 and NO2 again, so it's NO2 squared. And then what you would do is you would take your mechanism rate law and see if it matches the experimental rate law, and it did. So what that tells you is that basically, even though you don't know 100% sure that that is the correct mechanism, it's probably the correct mechanism. Next slide. So here's another one. So this one we're going to do the same way, and notice here that they gave us that step 1 is the slow step, and notice that we have 2 steps. So the way it would be written in your textbook would be this way. 2NO2 plus F2 is 2NO2F. And so somebody decided that they thought maybe this is the way it actually happened. When they did the experiment, they got a rate law of rate is K times NO2 times F2. And so they spent some time thinking about it, and they decided that maybe it happens in 2 steps. Here's step 1, and here's step 2. And when we add these together, add everything on the left of the arrows and then everything on the right of the arrows and cancel everything that's on both sides, we wind up with 2NO2 plus F2 on the left, and we have 2NO2F on the right. Now we also have this thing in red here on both sides. That's an intermediate. Remember we said that a while back? An intermediate is produced in one step, but then it's used up before you get finished. So it was produced here in step 1, and then it was used up at the beginning of step 2, so it doesn't turn out over here at the end in the final product. So when you add these together, the F's are going to cancel because they're on both sides. So we call F an intermediate. And let me just draw an arrow and point you back up here to the top. Okay, so if we add everything together on the left and the right, as I said, we get 2NO2 plus F2 gives 2NO2F. And so we want to look back at the top here and see if it matches what we had at the top, which is, we said, the way it would be written in the textbook. And if you look, you'll see that it does match. Then we want to see if the rate laws match. So find your slow step, and that's going to be this step right here, and multiply K times your reactants here. So the rate would be rate equals K times NO2 times F2. K, you always have to have the K. So the rate equals K times NO2, concentration of NO2, times the concentration of F2. And now look back up to see if that matches what they found experimentally, and it does. So both things work here. When we add up all the steps, we get the right reaction, and also the rate laws match. So it's very likely that this is the correct mechanism. Okay, next slide. And I'm going to let you guys read this on your own, and I'm going to go to the next slide. So a reaction is only as fast as its slowest step. So the way that we usually do it is we just assume that once the slow step happens, then everything else is going to be immediate. So in other words, we're going to basically say that the slow step determines the rate for the whole reaction, even if there's 3 or more steps. Next slide. And we've actually talked about this, so let's move on. Okay, so here's one. A plus 2B is C. We're supposed to have a mechanism that looks like this. And so we're supposed to write the rate law. So let's first of all, let's see if everything comes out. So add everything on the left-hand side of the arrow, and you're going to get A plus 2B plus D, and on the right you're going to get C plus D. But you're going to wind up with a D here on the right and a D on the left. So those will cancel. So what is D? Let me just ask you that question. So D is produced in the first step, but it's used up in the second step before we get to product. So D is an intermediate, right? So D doesn't appear in the overall reaction because it's made and used up. So to write the rate law, what we want to do is we want to look at the slow step and say rate equals some rate constant K times the concentration of the D times the concentration of the B. However, there's a problem because the D doesn't appear in the overall reaction. We prefer not to use it in the rate law. But there's a way around that, because if we look back at the fast step here, we can see that D is in equilibrium with A and B. And what I mean by that is, notice that this arrow is not pointing in only one direction. It's pointing in both directions. So in other words, we can say that D is kind of like in equilibrium with A plus B. And because of that, we can substitute A plus B, the whole thing here, for the D in our rate law, and write it as rate equals some rate constant K times the concentration of A times the concentration of B, and then times the concentration of B again. So it would be rate equals K times A times B squared. Now be careful here, because the rate law is confusing, because it looks like you should write it as rate equals K times A plus the concentration of B, but you don't write it that way. So don't let that plus sign confuse you. It's K times A times B. Let's go to the next slide. All right, so here is what we just did on the previous slide. Let's go to the next slide. So I'm saying here, and I'll let you read this on your own if you want, D is an intermediate, so we don't want to put that in the rate law. So we end up with this, which, let's go to the next slide. So we said that the D is an intermediate, so let's go to the next slide. So we end up that the rate is KAB squared, which is what we said about 3 slides ago. So if you don't quite get this, you can go back and pause the video on some of the previous 3 slides and look it over again. But the bottom line is that you're just looking at the slow step. So why was that last problem different? Well, it was because we ended up with a rate law that included an intermediate. So again, the answer here is going to be that the rate equals KAB squared. Let's go to the next slide. Here's one that I'd like for you guys again to do on your own. So notice here that we have this reaction the way it would be written in the textbook, and somebody has proposed a mechanism for that reaction that involves 3 steps. Step 1, step 2, and step 3. So what you're supposed to do here is see if this works. So you'll want to add everything on the left-hand side of the arrow, or arrows, and then the same thing for the right-hand side, and cancel things that are on both sides, and see if you get the same thing you got up here at the top. And if you do, then you go ahead and keep going. Go to your slow step and get your rate law, and then see if it matches the rate law that they gave you. So here, what you would want to do is you would want to come to your second step and write your rate law. So here's what's going to happen. You're going to get rate equals some rate constant K times the concentration of NO2 times the concentration of NO3. But there's a problem, because NO3 isn't in the overall reaction. So you're going to have to do what we did in the previous problem. You're going to have to figure a way around that. So you've got to find how to write NO3 in terms of something else. And so I'll let you do that as an exercise, and if you can't figure it out, just email me and I'll tell you. Next slide. Next slide. Okay, let's move quickly on now to the collision model, where we're going to wind up moving from this to the Arrhenius equation. The collision model, let's go to the next slide, is very complicated, and I remember when I first started grad school, we had this at the very beginning, and it's even actually a lot more complicated than what you're seeing here. But basically what I want to do is I want to break this down into its most basic parts, so you don't have to memorize this slide. What you want to do is just try to understand it basically, and then the things that you really need to remember I'll point out. So whenever you have molecules that are reacting, you have various different things that are involved, and let's go through them real quickly. The activation energy is just the amount of energy that 2 molecules would have to collide with in order to have a reaction. So it turns out that 2 things have to happen for a reaction to occur between 2 molecules, let's say, although it could be atoms. They have to have the right orientation, and they have to have enough energy. Okay, so let's move on from that. We'll come back to it later. The temperature also is one of the things that's involved, and the basic rule is the higher the temperature is, the faster things are going to be moving and the more energy they're going to have, which means that the higher the temperature is, probably the faster the reaction is going to go. And that's actually a rule of thumb in kinetics, is that if you increase the temperature, you increase the rate of the reaction. And the way that we usually assume that that happens is that you're increasing the rate constant K. And we'll see more about that in a moment. All right, so there's some stuff here that you don't really need to know. So let's get down here to this A thing. So what they're saying above this is that you have a certain number of collisions that are happening, which they're calling Z, but you don't need to remember that. And then you have a steric factor, P. Again, you don't need to remember this, which is how many of those collisions that are happening will have the right orientation. So if you multiply the fraction that have the right orientation times the number that are happening, you're going to get the number of collisions that happen with the right orientation. And that's called the frequency factor. And you might want to remember this one, or just remember that it's abbreviated as A. So A is like the fraction of collisions that happen with the right orientation. And then this thing is the other thing you'll want to remember, the exponential of minus EA over RT, which could also be written as 1 over E to the EA over RT, where the EA there is the activation energy, and the activation energy is the amount of energy that has to be present for the reaction to happen. R is the universal gas constant that we learned about in 1311, and T is the absolute temperature. And this represents, if you take the exponential, and when I say exponential, I mean e raised to the power of. If you take the exponential of minus EA over RT, you get the fraction of collisions that have enough energy. So remember, for A, we said this was the fraction of collisions that have the right orientation. And this is the fraction of collisions that have enough energy. So if you multiply A times e to the minus EA over RT, you're going to get the number of collisions that will have both the right orientation and enough energy. In other words, you're going to get the number of collisions, which we call K. So we can call K, and that's the same K we've been talking about the whole chapter. It is the rate constant. We can get that by multiplying A times e to the minus EA over RT, which that isn't on this slide, but we'll see it in a moment. Before we go any further, therefore, what I want to point out is that because this is actually e to the minus something, then we can rewrite it as 1 over e to the plus EA over RT. So what I'm going to say may not make sense unless you do that mentally. If we increase the temperature, we're going to increase K, because we're going to increase the rate of the reaction. So mathematically, it looks like if we increase T, because it's in the denominator of that fraction, it looks like it would actually decrease it, right? But it doesn't, because this isn't e to the plus EA over RT, it's e to the minus EA over RT. So things that you increase on the bottom actually end up increasing the rate of the reaction, which means that if you increase this thing on the top, it will actually decrease the rate of the reaction. So here's what I want you to remember. If you increase the activation energy, you make it harder for the reaction to occur, which means it slows the rate of the reaction. So let me say it again. If you increase the activation energy, you're slowing the reaction, or in other words, you're decreasing the K. If you increase the temperature, you're increasing the rate of the reaction, or in other words, you're increasing the K. Okay, so let's go on to the next slide and look at this some more. So here is our expression including the K. So K is just two different things multiplied together. The frequency factor, A, times this exponential term that tells us how many of the collisions have enough energy. So A, how many collisions have the right orientation, e to the minus EA over RT, how many of them had enough energy. Multiply those two things together and you get the rate constant. The rate constant is going to tell you how fast the rate goes. A big constant means you're going to have a fast rate. Again, if you increase the temperature, you're going to increase the rate of the reaction. But if you increase the activation energy, you're going to decrease the rate of the reaction because you're making it harder for this thing to happen. In other words, you're increasing the amount of energy they would have to react. Next slide. We've already talked about this, so let's go to the next slide. And this is just a repeat of what we just said, so next slide. All right, the activation energy here is the energy that you have to go over, like if you want to draw it this way, like if you're going from reactants over here to products over here, this would be an exothermic reaction because your energy of your products is lower than the energy of the reactants. This hill right here that you have to go over from there to there is called the activation energy. Next slide. Excuse me, and here we see it again. So remember we said that we could produce things that were called intermediates. So before we talk about that, so here's another picture of the activation energy. So it's just the energy between the energy level of the reactants and the products in this case. However, it could also be, if you're going in the reverse direction, it could also be the difference between that line and this line up here. Because if you're going from product back to reactant, you have to go all the way from this level all the way up to the top of that curve. Okay, so now let's talk about something else. We said that you could produce things that are called intermediates in a reaction mechanism, and intermediates can actually be isolated at times. So like, for example, when we were doing one of the reactions, I remember that one of the intermediates that we produced was NO3. It's possible in some cases to actually isolate those, and that basically is a way you could prove that it's actually involved in the reaction, right? But there are a couple of other things that happen during a reaction that you can confuse with intermediates. So very quickly, let's just point out the differences here. So when you're going from reactants to products, there's going to be a certain point where you're at a state that's like half reactant and half product. So some of the bonds are breaking and some of the bonds are forming. And if you want to look at actually what's happening here in this particular reaction, you can pause the video and just look at these graphs. So what I've got circled up here at the top, right at the top, I mean at the very tip top of that curve, is called the transition state, because you're going from the reactants to the products. Or if you're going in the reverse direction, you'd be going from products to reactants. So it's like when you're at that transition state, it could go either way, right? It could just revert back to the reactants, or it could go ahead and go on to product. There's one other thing that we have to talk about, and that's the activated complex. And the activated complex is where you're in this range. You're not necessarily at the transition state, which would just be that one point right there, but you're near it. You're kind of like at the top of that curve. So you're starting the transition process. So if you're going in the direction of reactant to product, you'd be going this way. So it's everything involved where you're starting to break the bonds of the reactants and form the bonds of the product. So it actually involves more than just the exact moment that's called the transition state, and that's called the activated complex. You probably won't be asked that, at least not in this class, but you may need that later on, and so this will hopefully help you not to get confused. Next slide. Okay, so here's some more explanation of that, which I'll let you read if you want. Let's go to the next slide. So that equation that we just wrote is called the Arrhenius equation, and it is K equals A times E raised to the minus EA over RT. So this equation is just the same equation that we had before, like 2 or 3 slides back. And you can actually use this equation here to solve problems. So for example, we know what R is, right? In this case, it's going to have to be the 8.314 form. And then if they gave you, for example, the T and the EA, and the A, then you could figure out what K is. Or if, in other words, we've got K, A, EA, and T. So we have 4 variables here where we're not including the R as a variable because we know what it is. So they could give you any 3 of those and ask you to figure out what the 4th one was, and they might do that, so that might be one way you'd see a problem. However, usually they don't ask them in this form. They usually do it in a different form where you're basically comparing what the rate constant would be at one temperature with the rate constant at another temperature. So you'd have a K1 at T1 and you'd have a K2 at T2. So it turns out that if we want to do problems that way, we have to do a little adjustment to this equation right here. And so what we're going to do is something we did before in 1311 when we were talking about Clausius-Clapeyron. We're going to take the logarithm of both sides of this equation. So on the left, we're just going to get logarithm of k. But on the right, we're going to get the logarithm of a times something else. Remember, the rule of logarithms is that the logarithm of a times b is the same thing as the log of a, or logarithm of a, plus the logarithm of b. In this case, the b is the e to the minus ea over rt. So what I'm saying is, if we take the logarithm of a times e to the blah, 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 then that can be rewritten, and it can be rewritten as the logarithm of a plus the logarithm of e to the minus ea over rt. When we do it this way, whenever you have the logarithm of e raised to some number, you just cancel logarithm and e, and you're left with just that exponent part, which is minus ea over rt, and that's what you see that's been brought down here, and it includes the minus sign. And then the logarithm of k is just going to come down here, and the logarithm of a comes down here. And the reason that they switch places here is because this way we wind up with another one of these y equals mx plus b, where x in this case is going to be not t but 1 over t, and y is not going to be k, it's going to be logarithm of k. But otherwise we still have our y equals mx plus b. So this actually represents another way that you could do problems where, for example, they could ask you what the activation energy is by giving you m. In other words, if they give you the slope of this line, then you can just set it equal to minus ea over r, where you know that this r has to be the 8.314 version of r because it's got joules in it, and you've got energy up here, so you're going to have joules here too. So that's a second way they could ask the question, but then there's another way. Let's go to the next slide. Okay, so before we do that, let's talk about this for a second. So here is the way we rewrote the Arrhenius equation in logarithmic form. So know here that the y is going to be logarithm of k. So we look over here, and they've graphed logarithm of k on the y-axis, and then the x-axis is not t, it's 1 over t. We saw something very similar to this with Clausius-Clapeyron. That was in chapter 11 of 1311. The slope is going to be minus ea over r, and then the y-intercept is going to be logarithm of a. Okay, now let's go to the next slide. All right, so if you do that for two different temperatures, you're going to get two different logarithm of K2s. Or in other words, you're going to get a K1 and a K2. So you could call either one of these T1 and T2, or T2, or you could call, and then for T1, you're going to have K1 and so forth. And then, so, I mean, I know this seems like we're doing kind of a lot, but we've actually done this before. So if we do this for two different temperatures, where we have a T2 here on top and a T1 on bottom, and if we then subtract this one from this one, and it really doesn't make any difference which order you do this in, but if just assuming that we did it this way, we would wind up with logarithm of K2 minus logarithm of K1 here, which we can then rewrite that according to the rules of logarithms, right? Logarithm of a minus logarithm of b can be written as logarithm of a over b. So that's just a basic rule that you should have learned in high school. And then when you do your subtracting over here, this is what you're going to end up with, where what they've done is they've multiplied through that parentheses by this minus sign. So you end up with a plus ea over r here, and then you just reverse these. So originally it was 1 over t2 minus 1 over t1. You multiply by minus 1, and you get 1 over t1 minus 1 over t2. And this is actually your basic reaction. Now, it may look like they did this wrong, but it isn't wrong. So if you take, originally you had t2 minus t1, but for the reason I just mentioned, it changes. So this isn't wrong. It's actually correct the way it's written. And the reason that we do this way is because we can solve certain problems this way more easily than if we try to use that original Arrhenius equation. So probably most of the problems you'll see for 1412 will be done using this formula right here. So both formulas should be on your formula sheet. So you'll just need to know which one to use. So whenever you're comparing a constant at two different temperatures, you'll want to use this one. On the last final exam, I had a question like that where I was asking people to compare the logarithm of the k's at two different temperatures, and this was the correct equation to use. And there was at least one person who tried to use the original Arrhenius equation, and you can do that, but it just takes forever, and he didn't manage to work his way all the way through the whole answer, and just wound up getting like 2 points out of 6 for that. So be sure you're using the right formula. So again, whenever you're comparing constants at two different temperatures, you want to use this equation, and it'll be in the formula sheet. Next slide. And let's go on to the next slide. So let me just read this. Chemists commonly use a rule of thumb that an increase of 10 K, or you could say 10 degrees centigrade, in temperature doubles the rate of reaction. What is the activation, or what must the activation energy be for this statement if you have an increase from 25C to 35C? So first of all, you're going to have to convert these from centigrade to Kelvin, because these temperatures in that formula have to be in Kelvin. Let's go ahead and move to the next slide. Couldn't get it to go there. So here is our formula from a couple of slides back. And the trick to doing this problem is, first of all, we know what the two temperatures are, so we can just calculate those. But again, they have to be absolute temperatures, capital T's. So you'll want to do that right off the bat so you don't make the mistake of doing the whole problem using centigrade, and then you have to go back and start over again. And we know what R is, so the only thing we don't know what is the K2, K1, and EA. And they don't tell us K2 and they don't tell us K1. The trick, and this is a trick, you have to remember this, is that you have to realize that what we're assuming here is that the K2 is going to be twice as big as the K1. So this is a little profound here. We aren't told what K2 is and we aren't told what K1 is, but we can figure out what the ratio of K2 is to K1 by realizing that it's twice as big, according to that rule of thumb. So for the whole ratio, even though we don't know either of these K's, for the whole ratio, we can just substitute the number 2. And that's how you solve the problem, because now we know everything except EA. So I won't go through the whole problem because we're like already kind of considerably over our time. In fact, I actually need to finish this up really quickly. So I'll let you go ahead and do the math here. It's just simple algebra. The trick to the whole problem is realizing that that is going to be a 2 right there, and that's why I put this in purple to mark it. So when you do the problem, you should get 53 kilojoules, but be sure and do it on your own. Next slide. And then catalysts, next slide. I'm going to go ahead and finish this. Catalysts are substances that speed up reactions without being consumed themselves. So you might see a multiple choice on the final or on my exam where it would just ask you maybe a fill in the blank where they just say what is a substance that doesn't get involved in the reaction but speeds up the reaction. And the example that's coming to my mind right now is an example from organic chemistry where you add an H2 molecule across a double bond, and that reaction is sped up considerably if you add platinum. And the reason is because the H2 molecule will kind of like lay down on the platinum in a flat way. And then when the platinum hits the double bond, it will just deposit one H on one side of the double bond and one H on the other side. So the platinum in that case would be a catalyst. Next slide. And it doesn't get involved in the reaction itself. So for example, here would be the reaction where you're trying to convert, let's say, ethene to ethane. If you didn't have a catalyst, it would be much harder to do the reaction. The activation energy would be higher than it would be if you use a catalyst. Next slide. And I'll let you look at this on your own so we can get done. I'll let you look at this one on your own, and this one also. So the other thing I want to mention is that enzymes are catalysts, but in biological systems, they don't call them usually catalysts, although they could, but they have a special name, and that's called enzymes. And let's stop here. So this is the end of this chapter 14 lecture notes, and so we'll still have the work problems to do, so I'll see you there.